let's discuss some properties of the Hamiltonian first, okay? First, the positivity of the energy. Now, it's very easy to show that the energy eigenvalues of the harmonic oscillator are positive. Okay, so how do we do that? Well, let's just revert back to the original variables for a minute. H is p squared over 2m plus half kx squared. Now, recall that if we have a Hermitian operator, say for Hermitian operators, if I have, say, psi, O hat, phi, now an identity is that if I take O over here, I have to make it complex. I have to Hermitian conjugate it, right? But since O is Hermitian, that means that this is equals to O psi of phi, right? So for Hermitian operator, we can write psi O hat phi equals to O hat psi phi, right? So now this means that if I take any psi and compute the expectation value of the Hamiltonian in that state, then what do we get? We get psi h hat of psi. Now h hat has two terms. One is the kinetic term, p squared by 2m of psi, plus half of k, psi x squared of psi. Now, we can take one of these operators, p squared, to this side. So 1 over 2m is a constant, so we can have p. So there would be a p dagger of psi, then p of psi, but p is a Hermitian operator, so we can get rid of the dagger. And similarly, x is also a Hermitian operator, so we can write this as x of psi, x of psi. Okay, you can put daggers, hats here if you want. Okay, is it clear what we have done?
Yes, sir.
So now let's just define a state phi to be p hat psi, and the state chi to be x hat psi. If I do this, then I see that h, the expectation value in psi, is given by 1 over 2m, this is a positive number, the expectation value of, the norm squared of phi, plus k over 2, another positive constant, the norm squared of chi. Now, since phi is non-zero and chi is non-zero, so that means that, this is greater than 0. Well, okay, mathematically what we mean is that we are not assuming that phi is 0 necessarily. Since this is greater or equals to 0 by definition, and this is greater or equal to 0 by definition, this means that the expectation value of h is greater or equals to 0. Okay? For all psi. Okay. Now, since h of psi is nothing but the expectation value of the energy, so the energy multiplied by the probability of that energy, so this is the probability. So, and here we have established this is greater than 0. But each of these are positive numbers, right? So that means each eigenvalue, EI, must also be positive. Okay? Because we can take this to be any energy eigenvalue. So if we choose psi to be psi I, then I will get the expectation value of h in psi I to be EI times P of EI, right? And this is greater or equal to 0. And because this is not 0, sorry, this is not negative, this is a non-negative number, that means this has to be a positive definite number. Okay? Okay, so I think, so we have shown that the energy eigenvalues of the harmonic oscillator is 0, is positive. Now, there are two ways of solving the energy eigenvalue problem. One is by solving the differential equation. So two ways of solving. Two ways of solving the energy eigenvalue problem. One is, solve the ODE. Solve the ODE using the series method. And this is a very good method, but there's a remarkably beautiful method, which is number 2 by Dirac. Solve by using ladder operators. Okay. So in next class, I will show you both. First, we'll do this, and it's a good method, but then we'll do this. Okay. If we run out of time, I will basically, make sure that if you have to go over time, we'll have to go over time to solve this show you these two methods. Okay. So we'll see you day after tomorrow for this, but I will see you tomorrow evening for assignment 2. Okay.
Okay, sir.
Okay. Any other questions?
I don't have a question, but I remembered in the intervening time that my Hume final exam is like from now till the 10th. So it's better for me if the final is on the 11th, but I'm fine with the final being on the 10th. I'll just have to finish it a day early.
What do you mean from now to 10th? Like how many?
It's an essay. Like it's a really long essay. So I have a week to finish it, something like that.
Okay, why don't you send me a message in a private and we'll figure something out, okay?
All right, cool.
Okay, all right. Okay, any other questions? So we have shown that the energy eigenvalues are positive. Okay, if not, I'll see you guys tomorrow.
So we proved that they were greater than or equal to 0, right? So, but we haven't discluded that they might be 0.
Yeah, they might be 0. We haven't. Okay. We are going to find exactly what their values are, but we actually will need this. We will need this result. We actually need this result to derive the energy eigenvalues. Okay. Because we will see in the ladder method. At some point, we basically will find a ladder. We will find a ladder of energy eigenvalues, and what we will find is that, there is a ladder, and in certain units, this is going to be 1. Okay? 1. So at some point, we will hit 0. Okay? Sorry, yeah. We won't hit 0. The fact that this ladder terminates will determine that we have to at some point hit 0. You'll see. It's an important piece in the puzzle. Okay?
Yeah, I saw glimpses of this in like an assignment that we did for linear algebra. It was a pretty advanced assignment, but it was pretty
No,
cool.
it's a very cool result. And if any of you take group theory in the future, you will see a generalization of this method in solving basically finding the representation of Lie groups and the algebras. Okay, and the generalization of this method gives you a way to solve the angular momentum problem in 3 dimension. And once you've solved that, that is one of the key results you need to solve. Find out the representation of any Lie group, any compact Lie group. So this method has very, very, very important generalization. Okay. So I don't know. Are you guys considering taking group theory next semester? Then you'll see how that. I will review that angular momentum method in that course. Okay, I think probably it's a good place to stop. If you guys have no other comments or questions.
Okay, then I'll take my leave.